Hello everybody, I am Nikhilesh, and in this series of videos, we'll be looking at this very classical problem from computational geometry called depth estimation. So we'll start by trying to understand what this depth estimation problem is and why it's important for us through a couple of motivating examples. Then we'll briefly talk about what makes this problem generally quite hard to solve efficiently from a computational perspective. And finally, we'll see that even though this problem is quite hard to solve exactly, we can in fact find an approximate solution using the power of randomness and sampling very efficiently. So that's the broad plan. We'll start by looking at two problems from computational geometry to help motivate this depth estimation problem. And the first problem we'll be looking at is called the range counting problem. So let's see what that's about. So what is range counting? So in this problem, we're given as input a set of n points. And as you can see in this image, I've represented these points using blue dots. But in general, in this image, these are represented as points in the 2D space. But in general, these can be elements in any space that you want. Then we're given a query set, which is also called a range in the context of this problem. And the goal is to count how many of the input points lie inside this range. So again, in this example, we have this orange rectangle, and this is our query range. And our goal is to find how many points lie inside this rectangle. Simple enough. So this is a very classical problem from computational geometry, and it has a lot of applications. So for example, let's suppose you have a database with you. And this database has information about a large number of people. And let's say you want to find out how many people have their age in some particular range and their salary also lying in some range. Now the idea is that you can think of this actually as a range counting problem in 2D. So here you can think of the x coordinate as representing a person's salary and the y coordinate represents their age. And so the question of finding how many people have their salary in some range and their age in some range is exactly the same as counting how many points lie within a particular rectangle, which is basically defines your age and salary ranges. So it's essentially the exact same problem that we have here. So, okay, so how do we go about solving this kind of a problem? Obviously, a naive way to do this would be to check for each of your n points whether the point lies inside your range or if it doesn't, and if it does, then count it one by one, essentially. And checking if a point is inside a rectangle is a simple enough task. You just have to check whether its x coordinate and y coordinate lie within some particular ranges. But this kind of manual counting of points one by one is going to take order n time if you have n points. The real question we have is, can we do better than this? Often in a lot of these kinds of database queries, the databases can be huge, and order n time is typically far too slow to be useful to answer these kinds of queries. So if we want to do better than this, one observation we can make is that typically in a lot of applications, the set of points is usually given to us upfront. Like in the database example, where you can think of all these records of people as something that we've been maintaining, and we have to answer a lot of incoming range counting queries that come in on this database. So one question we can ask is, can we pre-process the set of input points that we have somehow into some sort of a data structure so that we can answer these range counting queries more efficiently? And again, by efficiently, we're really looking to beat this linear time naive algorithm. And it turns out that in a lot of cases, we in fact can do much better with the help of some pre-processing. So for example, in this case where we looked at, where the points are in the plane and the query ranges are rectangles, there's this, in computational geometry, there's this very classical data structure called a range tree. And this range tree data structure uses linear space, so that is order n space, but it can answer range counting queries in order log n time. So this is quite a significant improvement from what the naive method that we have. And the space it uses is near linear. So basically, it's not much more space than you would need to just store all the points anyway. But the time complexity for answering a query goes down from linear time to log n time. So it's quite a significant improvement. So yeah, so in a lot of examples, we can in fact get some improvement. And finally, one thing to note here is that in the example I've shown in this image, these points are elements in the plane and the sets are rectangles on the plane. But in general, this range counting problem is also studied under a lot of other settings as well. So for example, instead of the ranges being rectangles, one other common motif under which this problem is studied is when the allowed range queries are half planes. So that is essentially you have a line segment and the goal is to count how many points lie either above or below the line. It's a line, not a line segment, sorry. And another example is if our ranges are disks instead. So you want to count how many points lie inside some disk or lie at a particular distance from some central point. And also apart from this, we also do quite frequently look at the higher dimensional analogs of these. So in general, in say D dimensions, we might be looking at how many points are there within a hyper rectangle or within a half space or a ball in D dimensions. And one interesting thing to note is that the kinds of data structures that we have to use to handle these different types of ranges are often in practice widely different. And in fact, these different problems for different types of ranges are often of significantly different hardness as well. So for instance, for rectangles, as I mentioned earlier, we can achieve this order log n query time with close to linear space. But however, suppose our query ranges are half planes instead, then it turns out, and we'll see this in more detail in a bit, that with linear space, it's impossible to achieve any kind of polylogarithmic query time. So in this sense, this half plane range counting problem is much harder to solve than the rectangle version. Okay, so that's the range counting problem. So now we'll look at another different problem called the point location problem in the plane. Okay, so here in this problem, the setting is that our input is a subdivision of a plane into a number of regions. So in this example that I've shown here, we have a number of lines that are drawn on the plane. And you can see that these lines divide a plane into a bunch of different regions or cells. Now, we're then given a query point, which I've marked as this blue point over here. And the goal is basically to determine which of these regions does this query point lie in. So in this case, essentially this query point lies within this pentagonal region that's formed by some 5 different lines. Now let's make this problem a little bit more concrete and define clearly what we mean by a region. So in this example, where the regions are defined by lines, we can essentially define a region as the set of lines that lie below the region. So why is this the right thing to look at? So for example, if I look at this particular blue point over here, we can define the region that this lies in using these 3 green lines that I've marked over here, which are the lines that lie below this point. And why is this sensible? If you take any point that's inside this pentagonal region, and we look at the lines that lie below it and the lines that lie above it, so any point within this region is going to have these same 3 lines lying below it. All the remaining lines, the black lines, are going to lie above the point. And if we take a point that lies in a different region, it's going to have a different set of lines that below it, that lie below it, and that lie above it. So in that sense, essentially knowing the set of lines that lie below this point uniquely defines the region in which this point lies. And so that's why it makes sense to think of the lines that lie below it as kind of an identifier of the region itself. So essentially, with this framework, we can boil down the point location problem to the following. Given a query point, find all of the lines that lie below the query point. Okay, now how do we go about doing this? It turns out that through some appropriate transformations and modifications to our problem instance, we can actually transform this point location problem into a simpler problem. Instead of finding all of the lines that lie below this query point, it turns out that it's sufficient if we can just count the number of lines that lie below this query point. And it turns out that the general point location problem actually does reduce to this counting problem. So we look at this counting version of the point location problem. So the goal, as I've stated here, is for any query point, we want to count how many points, how many lines lie below the point. And once again, similar to what we saw in range counting, as our input, we're given the set of n lines, and the goal is to pre-process this input set of lines to make solving these counting queries efficient. Okay? Okay, fine. So we've looked at these two problems. The first was this range counting problem, where given a range, we want to count how many points that lie inside it. And then this point location problem, which basically comes down to, given a query point, counting how many lines lie below the point. Now these two problems, they may appear to be cosmetically different, but despite that, it's quite clear that they share a lot of similarities. In some sense, all we've really done is interchange the roles of points and sets in between these two problems. So essentially, both of them are still counting problems, and instead of counting the number of points that lie in a set, we're counting the number of sets that lie below the point according to some kind of relation. It turns out that these two problems are similar enough that what we can do is we can actually define a more general problem that encapsulates both of these kinds of problems, range counting and point location. And that is what the depth calculation problem is. And we'll look at that now. So as I mentioned, this depth calculation problem is going to be a generalization of both the problems that we just looked at, range counting and point location. So let's now look at the formal general setup of this depth calculation problem. So as our input, we're given two things. The first thing is a finite set, which we'll denote calligraphic S. And the elements of this set, we'll call them objects. And the number of objects is n, because as I said, this is a finite set. Apart from this, we also have a second set called calligraphic R, and we call this the set of allowed ranges. Now this set of ranges might be infinite. You can think of this R as the set of all possible allowed queries. So for example, in the range counting problem, R can be the set of all possible rectangles, which is an infinite set. Or in the point location problem, R could be the set of all possible points on the plane, which is again infinite. Now for any range R, we're going to define the notion of its depth. So what does the depth mean? We'll denote the depth of a range R as mu subscript R. And this we'll define as the number of points, the number of objects that intersect R. And since we said that the set of objects is finite, the depth is also always a finite number for any range. And finally, the goal of this depth estimation problem is very similar in spirit to the previous two problems we saw. That is, given a set of n objects, the goal is to efficiently answer some depth calculation queries for any range in this calligraphic R. And so what we want to do is somehow pre-process these objects into a data structure that helps us to efficiently answer these queries. So, okay, just to convince ourselves that this framework makes sense, let's try to think about what depth means in the context of our two earlier examples. So, first of all, in the case of the range counting problem, our objects are points, and in particular, our calligraphic S is a set of n points that we're given as input. And the ranges are basically the set of ranges that we're allowed to run queries on. So depending on the problem instance, these could be rectangles, these could be disks, these could be half planes, etc. Now the depth of a range is defined as the number of objects that intersect it. And in this case, it exactly counts the number of points that lie inside the range. Because when we're talking about points, intersection is really the same as containment. So range counting for happens to be the same as depth calculation under this setup. And the second problem we looked at, the point location problem, we're interested in counting the number of lines that lie below a query point. Now, if we want to express this problem in this depth framework, what we can do is this nice little thing. We can define our objects as upward facing half planes for each of the lines. So we have these n input lines, and our objects are basically upward facing half planes from each of these lines. And our query ranges in this case are just going to be points. So if you look at the depth of a query point, it's basically how many upward facing half planes intersected. And it's exactly the same as saying how many of the lines lie below it. So essentially the depth in this case also corresponds exactly to the number of lines that lie below it, which is exactly the problem we wanted to solve. So in that sense, this point location problem is also a special case of this depth calculation problem. So okay, we have this generalized problem of depth calculation, which as we've seen looks at a number of different problems and kind of generalizes them all. And now that we've defined this notion, the next thing we're going to look at is we're going to start to talk about algorithms to solve this problem. So before we do this, a natural question we can ask is, how efficiently can we hope to solve this general depth estimation problem? And as I briefly talked about earlier, for some special cases like range counting of rectangles, we can actually answer queries in log n time with near linear space. But something to ask is, can we do this for any kind of depth estimation instance? And to understand this, we'll next look at some hardness results related to this problem. So now when we talk about the hardness of a depth calculation problem, there are really two factors to consider here. The first is the query time. The second is the space complexity of whatever data structure we use. And what we're really interested in is the trade-off between these two quantities, because really to improve the query time, we typically have to use more space and create larger data structures. So just to give an example, in the case of range counting with rectangles, there's this naive algorithm we first saw, which takes order n time to calculate the number of points inside a range just by querying checking each point individually. But on the flip side, this is very space efficient, since we're not really creating any additional data structure, and the amount of space is just linear space needed to just represent these endpoints alone. But on the other hand, what we can do is we can pay a small overhead in space by something like a polylog n factor, and we can construct this range tree data structure. And this range tree data structure can answer any rectangular range counting queries in order log n time. So in that sense, this is a pretty good trade-off. We've just paid an additional polylog n factor in terms of space, but we've improved the query time significantly from linear to order log n. So this is kind of like an efficient algorithm in some sense. However, it turns out that this kind of nice trade-off is in fact not always possible when we consider other type of ranges. So for example, when the query ranges are half spaces in D dimensions instead of rectangles, and we're trying to answer range counting queries, the trade-off happens to be much worse. And in fact, we have this result by Sunil Arya and David Mount, and that says that if we're allowed to use m space in total, then the query time that we have to incur, a lower bound of the query time that we have to incur, is at least n divided by n to the power of 1 by d plus 1, where d is again the dimension in which we work in. And this falls under the real RAM computation model, so we don't really count the individual bit manipulation time complexity. So what does this mean for us practically? Oh, sorry. Yeah. So if we look at 2D in R2 and we try to understand how well we can answer range counting queries for half planes, what this result says for that is that if we're allowed to use only linear or slightly superlinear space, then the query time that we can hope to achieve is only something like n to the power of 2 by 3 by this lower bound. Because if you, here d is 2, so in the denominator if you plug in m to be linear, so if you plug in m to be n, so it becomes n by cube root of n, which is n to the power of 2 by 3. So on the other hand, if we want something like order log n or order polylog n query time, then we would need at least cubic space, so n has to be at least n cube. So if we think about polylog n time as being efficient for answering these range counting queries, what this lower bound says for that is, unfortunately, if we want to answer queries in polylog n time, we are going to pay quite a significant cost in terms of space. We need to use at least n cube space if we want to do it that fast. So this is not that helpful. Now the natural question to ask is, can we somehow get around this? And a classic technique that we often use to get around these kinds of hardness bounds in computer science is to relax the problem a bit. We're essentially looking at something that's a bit too hard. So instead of finding the exact depth of a query range, what if we allow for some leeway and we say that it's good enough just to find an approximate depth instead? And in this case, can we do better? And this approximate version of this range calculation problem is what we'll call the depth estimation problem. So let's define this problem. So the setup is quite similar to the standard depth calculation problem. We have a set of n objects, calligraphic S, and then we have a set of allowed ranged queries, calligraphic R. But this time we also, in addition to these, have an additional error parameter epsilon, which lies in 0 to 1 as well. And our new goal now is, instead of finding the exact depth of a query range, we're happy if we can find the depth within an epsilon factor multiplicative error. So more formally, the goal is to output an estimate, which we'll call alpha R over here. And we want this alpha R to lie between the true depth, which we denote mu R, and 1 minus epsilon times the true depth. So in this expression, we've kind of written this as like a one-sided error bound. But we could have made this, we could have allowed for two-sided error as well. It doesn't really matter that much. And as before, our goal is to efficiently answer these queries. And we want to know if we can somehow pre-process these set of n objects into some data structure to answer these queries efficiently. So one small technical point to note here is that we're assuming that the error parameter epsilon is fixed upfront when the set of objects is given to us as input as well. So essentially we're building the data structure for a single error tolerance. It's not that each range counting query could have a different epsilon that keeps changing. So now the big question we really have to answer is, does switching to this approximate problem even help? So in particular for half space range counting queries, we saw that with linear space, we can only achieve n to the power of 2 by 3 query time. But now if we allow for some fixed multiplicative error, some fixed, if we fix some constant value of epsilon, then can we bring this query time down? And the holy grail that we're trying to chase is achieving this kind of polylogarithmic query time with linear or near linear space for half planes as well, similar to what we could do for rectangular range counting queries. So over the remainder of this video and the next video, we are going to try to build towards an algorithm to solve this depth estimation problem. So towards building an algorithm for this depth estimation problem, the first step we are going to take is to look at an even simpler problem than depth estimation, and that is the corresponding decision problem. And this is a very classic strategy in developing algorithms. So instead of solving an estimation problem, we try to solve a decision version of the problem first, and we can see if we can somehow reduce the estimation problem to just this decision problem. So what exactly is the decision problem that we're looking at over here? So as always, the input consists of a set of n objects, which we denote calligraphic as, the set of allowed query ranges calligraphic R, and our error parameter epsilon. But in addition to this, we also have an additional threshold parameter Z. So essentially, in this decision version of the depth estimation problem, the goal is something slightly different. In the actual depth estimation problem, we wanted to actually find the approximate depth. But in this decision problem, this is an easier problem. We just want to answer if the depth is greater than this threshold Z or less than this threshold Z. But we'll allow for this to be a little bit noisy. If the true depth is close to this threshold, it's okay if we make mistakes. So more formally, here is the decision problem that we're going to look at. So given a query range, we want to check if the depth of the range is greater than Z or less than Z. So in the exact decision problem, we have to basically output this exactly. We have to output, let's say, 1 if the depth is greater than Z and 0 if the depth is less than Z. But this approximate decision version, we're okay with making an error when the real depth lies within an epsilon multiplicator factor from Z. So formally, if the true depth is more than 1 plus epsilon times Z, we want to output 1. That is, we want to correctly say that the depth is more than the threshold. On the flip side, if the true depth is less than 1 minus epsilon times Z, we want to output 0. And finally, if the true depth lies within this epsilon factor band around Z, the algorithm is allowed to output anything. It doesn't matter. So here, this decision problem that we have defined here is clearly a simpler problem than the estimation problem, in the sense that the decision problem reduces to the estimation problem. So if we have an algorithm to get an estimate of the depth, then we can use that to easily solve this decision problem as well, by just checking if that estimate of the depth is greater than the threshold or less than the threshold. And that's going to answer this decision problem essentially. And if this estimate is correct within an epsilon factor, then the output of the decision problem will also be correct as long as the true depth is more than an epsilon factor away from the threshold. So because in this case, there's no risk of going over to the wrong side because of the error. The noise is not large enough for us to make a mistake. However, the interesting thing is, this also works the other way around as well. If we can solve this decision problem, then we can also use that to solve the original estimation problem. And that's what we'll see next. How do we do this? So I'm going to make the following claim, that if we can have an algorithm that solves this simpler decision problem, then we can solve the estimation problem as well using an order of log of log n by epsilon calls of the decision algorithm. So if you look at this quantity, this number over here, the number of calls, and think of epsilon as a fixed constant, this kind of looks like log n, and this grows very slowly with n. So what it's saying is that if we can solve the decision problem, then with a very small number of calls of this decision problem, just log n calls, we can also solve the estimation problem. And let's see how we can do this. So here is the main idea that we're going to use. So for starters, let's suppose we're trying to calculate the exact depth using an exact decision oracle with no error allowed for us. How do we do this? How do we do this if we try to solve the exact problem? So essentially, again, remember the thing is that let's say we're able to solve this decision problem exactly of whether the true depth lies above or below a threshold, and we want to use this to solve the actual depth calculation problem correctly. And the way we can do this is using a binary search. So we'll start with a threshold of n by 2, and we'll check if the depth is greater than n by 2 or less than n by 2. And based on the result, we'll go to the appropriate side and then we'll repeat this process again. And this way, if we want to find the exact depth, we'll basically need log n decision queries, since we're cutting our search space in half with every single decision query we're making. Now, but here we don't have log n, but we rather have something which is ordered log n calls of this decision version. And to bring this down from log n to log n, we'll crucially exploit the fact that we don't actually need to find the exact depth, but we're happy if we can find the correct answer to within an epsilon factor error. So to do this, instead of considering all n possible values for the depth, we'll construct an exponentially spaced grid of order log n by epsilon different thresholds, and we'll only consider these thresholds to be our possible estimates for the depth. And so when we run this binary search to find the correct threshold, instead of log n calls, is going to take log of log n by epsilon calls instead, since we're only dealing with this order log n sized set of thresholds that we're going to look at. So let's look at this in a little bit more detail. What we'll do formally is we'll define a grid of thresholds, Z1, Z2, Z3, and so on. And we'll define Zi as 1 plus epsilon to the power of I. So these are exponentially spaced. Now, how many distinct thresholds are there in this grid? Well, we're starting from our threshold being equal to 1, and then we're incrementing in powers of 1 plus epsilon. So essentially, and the maximum we can go up to is n. So the number of distinct thresholds we can have like this is at most log of n to the base 1 plus epsilon. And this is order of log n by epsilon. So we essentially have this grid of just log n by epsilon different thresholds. And now what we'll do is we'll define a critical threshold, Zi star, as the threshold where the decision problem changes polarity from 0 to 1. So more specifically, that is, it's the threshold for which the decision algorithm outputs 0 for the threshold Zi star, and it outputs 1 for the threshold Zi star minus 1. Now the idea is that if we can somehow find this critical threshold, then I'm going to claim that this critical threshold is a correct estimate for the depth within an epsilon factor error. And why is this? It's because from the way this critical threshold is defined, we've essentially sandwiched the true value of the depth from both sides. So you can work out that the true value of the depth has to be at least 1 minus epsilon times Zi star, and it can be at most Zi star itself. So the true depth lies within this small interval of range at most epsilon. And so Zi star is a valid estimate for our depth if we are allowing an epsilon factor error. And finally, how do we find this critical threshold Zi star? The naive way to do this would be to scan every one of these log n by epsilon different thresholds from left to right until we find a threshold at which this decision algorithm changes polarity. And that could take up to order log n by epsilon queries. But we can, if we become a little bit smarter, we don't really need to do that. Instead, what we can do is, instead of scanning all of these thresholds from left to right, we can do a binary search on these thresholds. So what we can do is, we have this log n by epsilon thresholds, and we do a binary search on these thresholds, and that is going to take log of log n by epsilon different calls to this decision problem. And using only basically order log n calls for a constant epsilon, we can solve this estimation problem as well. And so basically we've proven this claim. So if we can solve the decision problem, then we can solve the general estimation problem as well, with just a small number of calls to this decision algorithm. So from now on, we'll only focus on how to solve this decision problem. So okay, how do we now go about trying to solve this decision version of depth estimation? And what we'll do is, we started from our estimation problem, went down to this simpler problem of the decision version, and now we're going to go even simpler. We'll go from this decision version of the problem to an even simpler problem of just calculating range emptiness queries. So again, in the decision problem, we're given a threshold z, and we're asked to find whether the true depth is greater than z or less than z, and we have mistakes when the depth is close to z. This emptiness problem is something even simpler. All we need to do here in this problem is, given a query range, we just have to answer whether the depth is 0 or the depth is greater than 0. That's all. Whether it's empty or whether it's non-empty. So the setup for this emptiness problem is pretty much the same as the depth calculation problem that we looked at before. We're given a set of n objects, calligraphic S as always, and the set of allowed query ranges. And as I mentioned, the goal is just to determine whether the depth of the range is greater than 0 or exactly equal to 0. Or in other words, whether the range intersects any objects or if it intersects no objects. So if you think of this in the context of range counting, basically this problem is essentially comes down to answering whether a query range is empty or non-empty. That's it. And as we've seen over and over, the goal of this is to solve this efficiently somehow by pre-processing our input set of points. So this range emptiness problem is actually quite a well-studied problem in computational geometry in its own right. And it's been looked at for several kinds of ranges. So one example is for half planes and half spaces. So we saw that for exact range counting with linear space, there's a order n power 2 by 3 lower bound for exact range counting. But if we don't want to actually count the number of points and just want to answer this much simpler question of whether a half plane is empty or not, then for this problem we actually can do much better. And for this problem, we have this data structure that was constructed by Dawkins and Kirkpatrick. And this data structure they constructed is linear space, and it can answer half plane emptiness queries in just order log n time. So answering emptiness queries is possible to do efficiently in linear spaces for some sets of ranges like half planes. But how does this help us? The very interesting and surprising thing is that it turns out that in general, if we have an algorithm that can efficiently answer emptiness queries, then we can actually use this algorithm to solve the depth estimation problem as well. Actually estimate the depth as well. So this should actually be quite surprising. What we say here is that if we have an algorithm that's just able to answer whether a query range is empty or not, whether it has any points or not inside it, somehow that has enough power to actually be able to count the number of points inside a range to an arbitrarily high precision. And this reduction from emptiness to depth estimation, rather from depth estimation to emptiness, very crucially uses randomness and sampling. So in the next video, we're going to be picking up from here, and we'll see how we can use range emptiness queries to solve this depth estimation problem as well. And that's it for now.